So in last lecture, we introduced the op-amp, operational amplifier, and we said that that active device can generate power based on or from the source that we supply to this device. And we have seen that this power supply, those voltage ranges can vary from positive to negative. And we are using ideal op-amp where input impedance for the op-amp is infinity, output impedance is zero, and in this case, there are two rules that we will be using when we analyze circuits with op-amp. Those two rules are op-amp does not withdraw any current at its input, and the potential difference at its input is zero, which means that potential at its inverting input is the same as the potential as its non-inverting input. So we have seen the inverting amplifier and how to analyze circuits with inverting amplifier. We derived the output voltage in respect with the input voltage to the op-amp. Now, if we are to look at the second type of the amplifier, which is the non-inverting amplifier, if we want to apply the same rules before we do this, it is very important to keep in mind that the negative feedback has to be there. So if you look here at the output has been connected to the inverting input. And in this case, this is going to be for both cases of amplifiers, either inverting or non-inverting. So I am always taking the output and looping it into the input. Okay. So this is extremely important. Okay, so this is number one. So the negative feedback is there in both types of amplifiers. Okay, so what's the question? So what's going to happen here in the non-inverting, you see that the feedback is a negative feedback because it is connected to the uh, inverting input. And then from here goes to the ground. Then the input voltage is connected to the non-inverting input. And this is why we call it non-inverting amplifier. If we are to compare this with the the inverting amplifier, so this is the inverting amplifier. Can look at the difference between the inverting amplifier and the non-inverting amplifier. See, both of them, they have the same negative feedback. However, the voltage, the input is connected here through the R1 to the non-inverting input. However, here the input VI, let me call this one VI. However, the VI here is connected to the non-inverting input. So this is the difference between the inverting and the non-inverting. Both cases, the same rules applies where the current here is zero, the current withdrawn here is zero, and I have here V minus equals to V plus, and this one equals to VI, right? Because VI is connected to the non-inverting input. However, if I am to look here, this is 0, and this is also 0. And here V minus equals to V plus equals to 0 volt. Why? Because the non-inverting input is connected to the ground. So this is for those two cases. This is just to show you the difference between the this one is the non-inverting and this one is the inverting amplifier, right? Notice VI here is connected through the R1 to the inverting input, and that's why we're calling this amplifier as inverting amplifier. Notice that VI here is connected to the non-inverting amplifier, and that's why we're calling it an inverting amplifier. R1 in this case is connected to the ground. Okay, so again, if we want to derive the expression between the input and the output for the non-inverting amplifier, apply the two rules that we have talked about. So the current here is 0, 0, and I have here V plus equals to V minus equals to VI. So this means that V1 and V2 are also, well, the V1 equals to V2 equals to VI, because V2 is the V plus and V1 is the V minus as well. For the inverting, the relationship was negative, right? The the output was inverted. The output was 180 degrees shifted in phase, and that's why we had a minus. Now let's look here at the non-inverting amplifier and let's see what's this relationship. So we said V1 equals to V2 equals to VI. So this point here is indeed VI, right? VI. So if I am to apply KCL right at V1, so let's apply KCL. What do we get? We have I1 minus I1 plus I2 equals to 0. And in this case, I have I1 equals to I2, where I1 is 0 minus VI over R1. This equals to VI minus V naught, V naught over RF. Now, if you rearrange this equation, what are you going to get? So this one is minus VI over R1 equals VI over RF minus V naught over RF. Now, if you take this V naught over RF to the other side and take this one to this side, what do we get? We get V naught over RF equals to 1 over RF plus 1 over R1 VI, right? Now, this is So here, again, we said we have V naught over RF equals to 1 over RF, 1 over R1 VI, or V naught over RF equals to, so this one is R1 plus RF over R1 RF VI. Now if you multiply by RF, then you have V naught equals to R1 plus RF over R1 VI, or divide by R1, you get 1 plus RF over R1 VI. So this is the transfer function, or the relationship between the input voltage and the output voltage for the non-inverting amplifier. So this one for non-inverting amplifier. Go back to this slide. Okay. Now, the relationship for the inverting amplifier, just to remind you, was V naught minus RF over R1 VI. So this one for inverting amplifier. So this is the relationship between, for both types of amplifiers, inverting and non-inverting. Now, a special case from the non-inverting amplifier is what we call the voltage follower. So what does this voltage follower do? Now imagine I here put the relationship for the non-inverting amplifier, which was, if you recall, let me first draw the non-inverting amplifier again here just for convenience. So we have so the relationship here was V naught equals to 1 plus RF over R1 VI. Now, what's going to happen if I remove R1? Now, remember, this controls the gain, right? This is the gain. This is the gain for my amplifier. Now, if I remove R1, what's going to happen? R1 becomes an open circuit. So in this case, if I remove R1, if I remove this resistor, then R1 becomes an infinity, right? An open circuit, which means if I substitute here R1 with an infinity, then this one is going to be 0. So in this case, V naught becomes equal to VI, right? V naught equals to VI. And we call this voltage follower, or we call it buffer. So what does this circuit do, and what is the importance of this circuit? So regardless of the resistor that you have here, either a resistor or a complete wire like this, you're going to get the same performance. But what does this circuit do? This circuit is basically creating a buffer between your input signal, the circuit that is giving the input to this amplifier, and the output. So here, although V naught equals to Vi electrically, however, the source is different. This Vi now is existing at the input of this voltage follower. The equivalence of this Vi that is generated at the output of this voltage follower is not coming from Vi, it's coming from the power supply of the op-amp. And this is basically the purpose of the circuit, is to create a buffer such that your input signal will not be loaded. The op-amp is not going to take any current from it. He's going to see what's the signal at its input, and he's going to regenerate a signal from his own sources right at the output, such that V output equals to V input. So you can say that it is replicating whatever it is seeing at the input exactly right at the output. The only difference is it's creating a buffer. It does not load your signal, so the signal will not be deteriorated. The signal will be maintained, and a replica would be showing up right at the output of this voltage follower. Yes, it does not withdraw any current ideally from that signal. Yes. Okay, so moving on, let's do this example. In this example, as you can see here, we have a follower. I can see a voltage follower of non-inverting type. Just looking at the circuit and applying the same concept that we have talked about, the two rules that we have talked about. Don't let this wire that is looping from the output to the negative, to the inverting input of the op-amp cause any confusion to you. This basically means the following. If I apply the two rules, I know that the current here is zero, so there is no current taken from the output, right? And the current here is also zero. And what else do I know? I know that V minus equals to V plus equals to, can somebody tell me, equals to what? Equals to 3.7 volt. 3.7 volt. So in this case, now guess how much the voltage would be. Can somebody tell me how much the voltage here would be? Right at the output of the op-amp. 3.7 volt. This is correct. So look what happened to the 3.7. This 3.7 showed up here, equals to here. Because of this wire, it is also equal to here. So this point here has a potential of 3.7 volt.
Sure.
Yes, go ahead.
So there's 0 amps at both inverters, right?
Right, at both inputs. Why? Because I have an infinite resistance here. This resistance ideally is an infinite resistance, which basically means no current is gonna go through this resistor. That's why the potential here becomes equals to the potential. So if there's no current, so the voltage across this resistor that I called VD, if you recall, would be zero. And what does this mean? If the voltage here, VD, is zero, and this is V plus minus V minus. This means that V plus equals to V minus, right? Now, knowing the voltage right there at the output, 3.7, how do you think I can find now V naught? Can somebody tell me after I know now the voltage right there at the output of the op amp to be 3.7? Can somebody voltage division? Absolutely, you're absolutely correct. Can you give me the equation for the voltage division, please? You can use your mic if you want. 3.7 times 20k over 20k plus 12k, right? Yeah. So it's at the end the ratio. So we have here 20 divided by 32 times 3.7, which is V naught equal to 2.3 volts. Very simple. Just understanding the rules for the op amp, those two rules for the op amps, we managed to solve for the output of V naught, and the solution was one single equation, which is a voltage division equation. Now let's look at other types of op amps where we can use that op amp. So far, we have seen that we can use this op amp as an inverting amplifier and non-inverting amplifier, where I can control the ratio between the both resistors to change the gain. Now I can now extend this and not focusing on the amplification and just focusing on the mathematical operations that we've talked about earlier. We said that using this op amp, I can add, subtract, and this is basically what I'm going to show you here in this summing op amp. So this summing op amp is now able to add two analog signals together and show it right at the output of the op amp. So how does this happen? Now let's look at this circuit. In this circuit, we are using the negative, the inverting input as the input to my signals that I would like to add them. So let's assume that here, right at this node that I'm calling A, number one, the negative feedback is there. Yes, it is an inverting. Yes, this is inverting. Number one, the negative feedback is there. I always need to have this negative feedback. Number two, I have three inputs, as you can see, V1, V2, and V3, that each one of them is connected through a resistor, R1, R2, and R3. So for me, looking at this, I can say that all what I'm coloring here in red are one node, right? All what I'm coloring here in red are considered one node. Fine. So if I apply those two rules that I have talked about earlier, basically I can see that the op amp is not gonna withdraw any current. All the currents entering into the op amp are 0 ampere. So what else? The second rule is, we said the V minus equals to the V plus. And in this case, I know V plus is connected to the ground, which means that this is going to be 0 volt. It's very clear now to me. I can see that clearly, that the V plus is 0 and the V plus equals to V minus. So V minus is 0. So the voltage at this red node here, this whole node is 0 volt. Do you agree? Fine. So in this case, if I am to write the KCL right at the node A, what do I write? I would write the following. I have I1 entering, I have I2 also entering, I have I3 entering, and I have I leaving with the 0, which means that I equals to I1 plus I2 plus I plus I3, right? Now, if I am now to go to this, and see what's this I1 and I2. So here, what is I? I have I to be, so this one is 0, we said 0 volt. I have I to be 0 minus V naught over RF. I have I1 to be V1 minus 0 over R1. I have I2 to be V2 minus 0 over R2. And I have I3 to be V3 minus 0 over R3. Or V naught, if I multiply by negative RF, what do I get? I get minus RF over R1 V1 minus RF over R2 V2 minus RF over R3 V3, right? Now, here, if I assume that those R's, R1 equals to R2 equals to R3, give them R, then in this case, V naught would be, I can now take minus RF over R, and I will be ending with V1 plus V2 plus V3. So equating those R's basically is going to give the same rate for each of those voltages. So I can take my now minus RF outside. And as you can see here, I managed to come up with a function that can add those inputs. So let's assume if you have an input of 1 volt for V1, 2 volt for V2, 3 volts for V3, then the ratio here would be amplified by this, of course, inverted by the minus, and the total would be minus whatever this gain times the summation of those three inputs. If R's are different, then it is a gain for every one of them, right? If R's are stays the same, so it depends. V1 would be added, but multiplied with a different gain. So you can see here the gain A1 is different than the gain A2 is different than the gain A3. By doing this, I managed to made gains to be equal. We started with the current. We don't want to go back to the current. We're talking about the voltages, right? It's already the currents, yeah. So we started with the currents. So the currents are added anyway, but we're trying now to relate it to the voltages, and we said that here based on the gain. So if I make R1 equals to R2 equals to R3 equals to RF equals to R, in this case, then V naught would be minus V1 plus V2 plus V3. So in this case, I have a unity gain for each one. Okay? So this is for the summing amplifier. Now let's move on to the next operations that we can use, which is the subtraction between those two inputs. So in this case, I have, as you can see here, both inputs are used in the in the summing amplifier. The inverting was the input that had all those currents going through, while the non-inverting was connected to the reference point. Here, I am using both inputs. I'm using the inverting and I'm using the non-inverting as my inputs to my signals. And this is what we call the difference amplifier, where here I am looking at the difference between those two inputs. But how to derive this function would be with the following. So here, as you can see, I have for the inverting, I have first input V1 is connected through R1, and I have the negative feedback as well. So negative feedback is essential here. Then for the non-inverting, I have the second input V2 is connected through this resistor R3, and then this R4 is connected to the ground. So how can we derive this transfer function? How can we derive the relationship between this output voltage and the two input voltages? And then we can see the difference amplifier. So this is the relationship that we would like to derive. So let's derive it together. At the beginning, based on understanding the two rules, no, I will not ask you to derive it in the exam, but you will be probably required to do some analyses, but not. I will not ask you to derive the difference amplifier or the summing. But again, those techniques you're learning to apply them in order to do some circuit analyses on op-amp. So let's look at those two rules that we talked about. The current equals zero, so the op-amp is not going to withdraw any current, and I have V minus equals to V plus. So this is very important. Those are the two rules that you always need to start with. So let's start first here. What is the V minus? What is the V? I can see that VA and VB are the V minus and the V plus, which basically I'm going to say now here, VA equals to VB. So I will start from this V2 because I know here the current is zero. So this is as simple as, can somebody tell me how to calculate VB? how do we calculate VB? Yes, we know VA equals to VB, but now what is VB in terms of V2? Remember, now I need to relate everything to V1 and V2. So what is VB in terms of V2? VB is V2 over R3. It's, it is R4 because VB is the voltage drop across this resistor. So it is R4 over R3 plus R4 times V2. Remember, your reference is the ground. Whenever you measure the potential, you're measuring with respect to your reference, and your reference is here, not here. So I have VB equals to V2 R4 over R3 plus R4. I'm done with VB. Now I need to derive the relationship for the second input, which is the inverting input. Can somebody tell me how to write the equation? I would say KCL at A or at VA. And this KCL is, now we know I1 equals to I2, right? Great. Can somebody give me I1? What is I1? I1 is, no, no, think about it. It's the current initiated from where, going to what are the nodes that this current is going from, ending at? V1 minus what? V1 no, it's not zero. Is the potential here zero? Exactly. It's V1 minus VA divided by R1. So V1 minus VA divided by R1 equals 2. What about I2? We're looking at the voltage, right? No, 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 no. This zero current means there is nothing going in here. This zero current, as you can see here, means that I1 is going to continue all the way, move up. And that's why I1 equals to I2. What is I2? I2 is VA minus V naught over R2. Exactly. So this one is VA minus V naught over R2. Let's rearrange. So if I am to rearrange, this is going to be R2 V1 minus VA equals to R1 VA minus V naught. Then R2 V1 minus R2 VA equals to R1 VA minus R1 V0. Okay, so what I am going to do, I will move this to the other side and bring those two to this side. So here I have R1 V0 equal to R1 VA plus R2 VA minus R2 V1. Is that right? Then R1 V0 equals to, take the VA outside. So I have R1 plus R2 VA minus R2 V1 divide by R1 V0 equals to R1 plus R2 over R1 VA minus R2 over R1 V1, right? Or V0 is R2 over R1 plus 1 VA minus R2 over R1 V1. We have here VB now. We said VB equals to VA, so I can substitute now VB here and VA. So substituting 1 and 2, what do we get? V0 equals to R2 over R1 plus 1 and then R4 over R3 plus R4 V2 minus R2 over R1 V1. V0 equals to R2 over R1 plus 1 and then R4, this is basically means R3 R4 divided by R4 V2 minus R2 over R1 V1. Now if we continue, then we have V0 equals to R2 over R1 plus 1 over, we can say here R3 now over R4 plus 1 by cancelling R4 with R4. This one equals to V2 minus R2 over R1 V1. Now if we take R2 over R1 outside, what do we get? This becomes V naught equals to, take R2 over R1 outside, we get 1 plus R1 over R2. Also, we can change this one to make it look the same, R3 over R4, V2 minus R2 over R1, V1. Now, if we assume that the ratio of R1 over R2 equals to R3 over R4, here, those resistors, R1 over R2 equals to R3 over R4. In this case, I can now cancel this. So if R1 over R2 equals to R3 over R4, and this equation can be simplified to the following. So this is V naught equals to R2 over R1, V2 minus R2 over R1, V1, or V naught equals to R2 over R1, V2 minus V1, and this is the difference amplifier. So in this case, the output of this circuit would be equals to the difference of V2 and V1 times the gain of the amplifier that is defined here by R2 over R1. So this is the difference amplifier. So what is the advantage of the difference amplifier here? The difference amplifier will be able to cancel any common signal that do exist on both inputs. So we'll eliminate whatever noise that will be picked up and exist at both inputs. Any signal that is undesired to exist and do exist on both inputs will be cancelled in this case. And now I will be getting this transfer function that defines the difference amplifier. And as I said, in difference amplifier, we call this the common mode rejection, where basically any common signal that do exist on both inputs will result into being cancelled because it will be part of V2 and also part of V1, and it will be cancelled due to this difference amplifier that is defined by this transfer function. Okay, so now the instrumentation amplifier is another type of difference amplifier. However, here we have all those resistors, R3, for example, that that belongs to A1, and R3 that belongs to A2 are manufactured in the chip itself. So in this case, the tolerance would be way better than any difference amplifier that you have those resistors outside. So in this case, the difference amplifiers is defined by A3. So if I am to put this dash line here, this is A3 here, and this A3 defines the difference amplifier. And as you can see here that this is the ratio between R1 here, those are equal, which means that the ratio is the same in this case. So having said that, you can notice that the input for the difference amplifier here is V naught 1 and V naught 2 and V naught 2. So you can notice here that the input for the difference amplifiers are V naught 1 and V naught 2 here. Those are the input for the difference amplifier, and those inputs are also connected uh, um, uh, ac- uh, between those three resistors that are in series, R3, R4, and R3. Now, A1 and A2 are going to work as a buffer to isolate the signal, and R4 here is going to be used to control the gain of this part of the gain equation uh, for this instrumentation amplifier. So now if we go to stage number 3, which is the A3 here, we can see that the difference transfer function for the difference amplifier do exist here with those inputs V02 and V01, right? However, the A1 and A2 are working as a buffer in front of the signals, and they have this current I. Now, if I delete this one just to show you the current I here. Now, I need to create a relationship between those V01, which are the input for the difference amplifier, and the real inputs to my instrumentation amplifier. So how do I do this? So let's derive this together. So here, if we said that the difference amplifier is defined by this transfer function V0 equals to R2 over R1 times the difference of the input, and we know here though that those inputs are V02 minus V01. Again, I need to come up with a relationship between my output and my input, which are V1 and V2. So in order to do this, I need to make use of the two rules that we have learned earlier. So if I come here and I say, this is my node here, all those are one potential. And I will do the same for this one, all the nodes with this potential, as you can see here. So what did I do in this case? I managed to find the relationship between VA and V1. Why? Because now, since they are the same potential here, then this node that is called VA is indeed V1. So I know that VA is V1. And I also know that VB is V2. VB is V2. So now, if I think about those three resistors that are in series, and keep in mind that the current here going in this branch is 0. What does this mean? This means that this I is going through all those resistors, and that's why those three resistors are considered to be in series, which means that this current I can be written as V naught 1 minus V naught 2 divided by R3 plus R4 plus R3. Is that right? And this current I is also can be written as VA minus VB over R4. So this current I is also the same in R4 as VA minus VB over R4. But what is VA and VB? VB is V2. VA is V1 and VB is V2 over R4. So in this case, I can equate those two, and in this case, I will get V naught 1 minus V naught 2 over 2R3 plus R4 equals to V1 minus V2 over R4, or V naught 1 minus V naught 2 equals to 2R3 plus R4 over R4, and this is V1 minus V2. I can simplify further, and I can say V naught 1 minus V naught 2 equals to 2R3 over R4 plus 1 V1 minus V2, or V2 V naught 2 minus V naught 1 equals to 2R3 over R4 plus 1 V2 minus V1. So this is 1, this is 2, then substituting 2 and 1, we get V naught equals to R2 over R1, 2R3 over R4 plus 1 V2 minus V1. So this is the relationship for the output voltage in terms of the input voltages for the instrumentation amplifier. Okay, this is what we have derived. Okay, so now let's move on. And as you have seen, in operation amplifier, since the input impedance, the input resistance for the operation amplifier is ideally is infinity, in this case, this operation amplifier will not withdraw current from the previous stage, and in that sense, I can cascade several operation amplifiers, and I can calculate the output based on the input, knowing the gain of the first stage, and then I can calculate the output at the second stage by taking this output from first stage as input to my second stage, and as you can see, and then at the end I can say that the V output is the gain of the third stage times the input, which is the V3 of the previous stage. So in this case, I can say V naught equals to A3 V3 or A3 A2 if you substitute V3 with A2 V2, or A3 A2 A1 V1. So as simple as this. Now let's do this example to demonstrate this concept. In this example, if I look at those two op-amp, I can see that the output of the first, so let me draw a dash line here just to show you what do I mean. So if I call this one stage 1 and this one is stage 2, I can see that the output of stage 1 is going into the non-inverting input of the second op-amp. So looking at the stage 1, I can say that stage 1 is a non-inverting amplifier, that its output is connected to the also positive terminal, which means that I have here two non-inverting amplifiers that are cascaded. So in this case, if I put the equation for the non-inverting amplifier, the general one, if you recall, which is V naught equals to 1 plus RF over R1 VI. Now let's look at the stage number one. Stage number one, this is my VI. So here I know VI as 20 millivolt. And what else? I know that RF is a 12. This is what I know, 12K. And I also know that R1 is 3 kilo ohm. So, and V naught here is indeed the voltage at A. So I can call here also VA as V naught for this first stage. So this is stage one. If I substitute now all this into this equation, I get VA equals to 1 plus 12K divided by 3K times 20 millivolt. And in this case, if I calculate, this is 12 divided by 3, 4 plus 1 is 5. So the VA here would be 100 millivolt. So this is my VA. Now this VA is going to be the input now to the second stage. So now let's put stage 2, which is also a non-inverting amplifier. So stage 1 and stage 2 are both non-inverting amplifiers. However, for my stage 2, I know RF is 10K. I know R1 is 4K. And I know VI as VA, which is 0.1 volt. Now, if I V naught is going to be the same because this is the last voltage here. So I have V naught equals to 1 plus 10K divided by 4K times 0.1. Now, if you do the calculation, you will see that V naught is 0.35 volts. We also need to calculate the current I naught. Look at the current here, I naught. This current I naught is going this way, which means R4, which means the 4 kilo ohm and 10 kilo ohm are in series only because there is no current going here. So since there is no current going here, this I naught is going through this whole path through the 10 and 4 kilo ohm, and I can now say that I naught equals this potential difference, which is V naught divided by 10K plus 4K, or V naught equals to 0.35 volt divided by 14 kilo ohm, and I naught equals to 25 microampere. Okay, so this is my last slide, which is basically the summary of what we have seen so far in op-amp. So we have seen the open loop op-amp, where the relationship was given by the open loop gain, and then we said that we have to use a negative feedback in order to have a control on the gain, in order to compensate for the bandwidth of operation. And then we introduced the two rules. We said that the operation amplifier is basically a voltage controlled voltage source. And then we've seen how to amplify a signal using inverting amplifier, and how to amplify it using non-inverting amplifier. So those are the two expressions. This is the gain for the inverting amplifier. This is the gain for the non-inverting amplifier. And then we've seen how to do mathematical operations like the summing amplifiers, the difference amplifiers, and also how to implement the difference amplifier into the instrumentation amplifier to achieve better signal quality due to the way higher resolution that do exist in chip fabrication instead of using resistors on a PCB. So lots of parasitics would be eliminated. Way better quality signal can be achieved from instrumentation amplifier, and then we solved an example to show you how we can cascade different amplifiers. You can still do this between different types of amplifiers. They don't have to be from the same type. You can have a follower with non-inverting. We can have inverting with non-inverting. That's just okay, as long as you know how to apply the two rules that we have discussed and we talked about earlier. Thank you. We'll see you in next lecture.